In this video, I'm going to show you how to use a graphing calculator to carefully examine the graph of a given function. We're going to use an example taken from the section titled Functions and Their Graphs, in particular number 60 right here, which you can see on the screen. And if you have a calculator handy, it may not be a bad idea if you were to pause the video and key this function in so you can sort of follow along. So the instructions for this problem says, in problems 53 through 60, use a graphing utility, for us that would be a graphing calculator, to graph each function over the indicated interval and approximate any local maximum values and local minimum values. Determine where the function is increasing and where it's decreasing. Round answers to 2 decimal places. Now notice the interval they're giving us here is from -3 to 2. So let's key this function in. Now the calculator is programmed to understand the order of operations agreement, and so if you're able to get the same results and you're not keying in the function the same way that I do, then it's all good, don't worry about it. When I key stuff in, I tend to look for clarity, and I want to make sure that I use complete syntax so there's no misunderstanding. And so I would key it in this way. We have minus 0.4 times x to the 4th power minus 0.5 times x cubed plus 0.8x squared minus 2. So now the function is keyed in. Probably the best thing to do at first when you're working with something like this is to take a look at a good zoomed out view. So in other words, you can be sure you're seeing what you need to see. So you can quit this here, and the best view for that, generally speaking, would be the standard zoom, which is giving you a screen that goes from -10 to 10 on both axes. And now you can see that the calculator is graphing the function. Now this isn't a bad view, but it is zoomed out, and it makes it a little bit harder to see what's going on. So I think it would be best to change the window size. If you recall, in the problem they told us that the interval they want us using on the x-axis is from -3 to 2. And so I'm going to use that as my interval. And when you look at it again, it's a better view, but still there's some wasted real estate here because this particular function doesn't go above the x-axis. So there's really no reason to be looking at this portion of the graph up here. It's wasted space. And so I would change the window a little bit more to make this nicer. I'm going to change my y values, and instead of going from -10 to 10, I'm going to go from -4 to +1. And it's worth to mention the values that you see here, x scale equals 1 and y scale equals 1, those give you the distance between the hash marks on each of the axes. So on the x-axis, the hash marks are 1 unit apart, and likewise on the y-axis, the hash marks are 1 unit apart. Here's our graph. Now this is a much nicer view, and when I'm looking at this, I can see that I have a local maximum somewhere around here. I have a local minimum somewhere around here, and I have another local maximum somewhere around here. Now many people will look for these using the trace function. They know that they can push the trace key and they can use the arrow keys to motor along the graph. And if you're a very skilled user of the calculator, you probably could make this question work, and you could answer everything using the trace key. But the problem with the trace key is that its accuracy is dependent upon the size of the window. And so for most people, the trace key is a bad choice because you're going to end up getting your answers wrong, at least partially wrong, in MyLab. And so the calculator has built-in functions, and that's what the text is encouraging you to use, and that's what I would encourage you to use. They're much more accurate than using trace. So how do you get to those functions? Well, you use second trace. It takes you to the calc menu, and you can see that function number 3 and function number 4 are for finding minimum and maximum values, respectively. So if we go back to the graph, we are looking for this maximum right here. So to find it, you'd go second trace, you'd hit number 4 for the maximum function, and you can see that the calculator is asking you to locate the maximum. It wants a left bound and it will want a right bound. So this is -1 on the x-axis here, and this is -2, and those look like they would be good boundaries. So I'm going to use -2 as my left bound. I'm going to use -1 as my right bound. And now the calculator is asking for a guess, meaning that you can use the arrow key to get close to where the maximum is at, or you could just put in a value. So in this case, I'll put in -1.5 and then press enter. And so you can see that the calculator is returning the value here, -1.57 and -0.52 for y. So you might want to jot that down. We were instructed in the problem to round to 2 places, so the x-coordinate would be -1.57 and the y-coordinate would be -0.52. The next thing we want to find is the local minimum that's over here somewhere. So we go back to the calc submenu and we use the minimum function, and again it wants a bound, a left bound and a right bound. So I'm going to use -0.5 and 0.5. And as far as a guess, this is an interesting example because you can get to see a little bit of round off error in the algorithm here. If you use the arrow key, let's say you think that it's over here somewhere, so you take the cursor there and you press enter. You'll notice that the calculator is giving you a value here which does not look like it's 0. But if you think about that value, this is given in scientific notation, so this is, in other words, the calculator's way of saying 5.417 times 10 to the -7. And if you were to render that value in decimal notation, that would be a 0 point and then followed by 6 zeros and then 5417. So in other words, if you're rounding to 2 places, that's 0. And the calculator will actually give you that if you send it in the right direction, but because of the algorithm that it's using to locate this minimum value, there's a little bit of round off error, and so that's why it's giving this value here. But understand, it is 0. And you can see that if you try it again. So in that case, it's giving you the clean form of it because basically you told it where to go. In any case, you probably want to jot that down as well. The value you would record would be 0, -2. And we were saying that over here somewhere there's a local maximum, and so we need to find that next. For boundaries, I'm going to use 0.5 and 1. Let's try that again. Here's our graph and maximum. So the left bound that we're searching for would be 0.5. The right bound would be 1. And I would guess it's at 0.75, something like that. And so you can see that the value that the calculator is returning is 0.635 and change. So if I was writing this down, I would write down 0.64, comma, -1.87. Let's take a look and make sure we're answering the question here. It says, tell us where the extrema are and tell us where it's increasing and where it's decreasing. So we go back to the graph, and the function is increasing as you come into the local maximum. And at the local maximum, it is neither increasing nor decreasing. It's effectively flat there, if you will. And so it decreases from the local maximum down to the local minimum here at 0. And then it resumes increasing to the local maximum. And then it resumes decreasing as you head off to 2 on the x-axis. So if you're rendering those as intervals, and you're telling MyLab what the intervals are, you would report from -3 to -1.57, the function is increasing. From -1.57 to 0, function is decreasing. From 0 to 0.64, it's increasing. And from 0.64 to 2, it's decreasing. Here's what you should have for your answer. So again, we had a local maximum at negative 1.57 and minus 0.52. Another one at 0.64 and negative 1.87. We had a local minimum at 0 and negative 2. We were increasing from negative 3 to negative 1.57, and again from 0 to 0.64, and we are decreasing on negative 1.57 to 0, and from 0.64 to 2. Hope that helps. If you have any questions, please feel free to drop me a line.